Hey everyone. Today we are going to graph and analyze rational functions. So in the last video, I talked to you about trigonometric functions and how they're really cool for modeling things that have periodic changes, like my blood sugar going up and coming back down, or a sound wave that travels along and has an amplitude. Lots of other relationships. If I had a pendulum swinging back and forth, I could measure its distance from the center. It gets bigger and then back to zero and bigger and back to zero. That would be another thing. So I'm going to show you another type of function that is very important in calculus. We're going to analyze rational functions. They pop up in pre-calculus. We saw them in accelerated integrated 3. And rational functions, you must think, wow, if trig functions are so useful, rational functions must equally be as useful. They're not as useful for modeling real-world behavior and stuff we're going to look at. Instead, they are an important function to allow us to explore important things when we're talking about functions in general. So the cool thing about rational functions is they can have a lot of problems with them. We can have a lot of what's called discontinuities when we begin to study them. And that's going to be important for calculus, is knowing when functions have discontinuities, when we have asymptotes, when we have end behavior changing. So that's why we need to be able to analyze them. So we'll be working on that. I'm going to show you 2 examples to try to remind you of how things work. And then next class, you will work on these in your performance task, and you'll be working on them as homework, some of the more basic ones. So the one I want to look at, I'm going to call the first one g of x. So g of x equals a rational function. What does it mean to be a rational function? Well, it means you have a variable, your independent variable, in the denominator. It might be in the numerator too, but it definitely is in the denominator. So this one's more advanced, more sophisticated. I'm going to skip some of the more basic ones because I think you remember some things about them from last year. I'm going to go straight to kind of the intense ones and all the things I want you to be able to do with them. So the first thing you should always do before you even move on to the analysis, I want you to factor if you can. So if you can factor, you should factor. Use whatever strategy you like. I'm hoping at this point you can kind of do it in your head a little bit, but if you like your area model and all that, go for it. I think the top factors is 2x and then x, and then I think there's a 1 here. There's got to be a 1 here. So we want a minus. So it's looking like a minus situation. In the bottom, this one factors as, looks like we want an x and a 1, an x and a 3, and we want a plus 2, so this is the plus, this is the minus. All right, so factor first, and the reason we do that is because a lot of times in this class, these problems are designed for it to become a nicer problem. So a lot of times we're designing the problems so that something nice happens. And in this case, you have an x minus 1 factor in the top and an x minus 1 factor in the bottom, so those can divide each other out. And really, we are left with, running out of room, as I did the last time. I'll come write it down here. Once the x minus 1s cancel, sorry, I cut off myself, but you are left with this. That's the function we are left with after we cancel, but there's an important note about this, x minus 1. So I'm going to change it up a little bit this year. The first thing you should do is talk about holes, if there are any. So how do you know if there's a hole in the graph? Well, there's a hole if some term canceled out. And in this case, it did. So because this term canceled out, to find the hole, you set the canceled term, set it equal to 0. And we can solve for where the hole is in the graph. So in this case, we have a hole at 1. So at x equals 1 in the graph, there's going to be a hole. If you wanted to find the actual coordinate location of the hole, you would plug 1 back into the simplified function, 2x minus 1. So I want to find the coordinate, so I'm going to plug 1 back into the simplified, and I get 1 up top and 4 on the bottom. So that's the actual coordinate location where the hole is located. One other thing before we move on, we're going to learn this down the road, but you may as well get an early jump. Holes are, the pre-calc way of talking about them, removable discontinuity is how we're going to start talking about them in this class. Removable discontinuities. There's a reason they're called removable discontinuities. It's kind of like you removed the problem or the issue with this graph from the problem. So you see when we graph it, holes don't really cause big issues. When we graph it at the very end of all this, you'll see that the hole doesn't really cause the graph to do anything funny. It's almost just like a chunk was taken out. So holes are definitely something you want to find, and let me know if they are existent in the function. Let's move on to the second thing. So the second thing, from here on out, we can work with our simplified function, which is right here. I'll rewrite it down here again. So this is our simplified function. We're going to work with this from here on out. I'll keep rewriting it because I'm going to keep going down. So one of the things that we are going to do a lot in this class is find the roots or the x-intercepts. So roots. I like roots. It's just a simple word. It means x-intercepts though. Okay. So what are the roots of any function? Well, to find the roots of any function, just set the function equal to 0. So we're going to take our function over here, and we're going to set it equal to 0. So this is where you may have heard in other classes, oh, can't you just set the top equal to 0? Yes. By setting the numerator equal to 0, it doesn't matter what the bottom is. Think about if you have a fraction. 0 out of 4 is still 0. 0 out of 20 is still 0. 0 out of 50 is still 0. So it's the top of the fraction equaling 0 is when we have roots. So we can just set the numerator equal to 0 and solve that out. And we'd add 1 divided by 2. There's my root, only 1. Sometimes we'll have 2, sometimes we'll have 0. In this case, we had 1 root. So far we know there's a hole in this graph at this location, 1 1/4, and we know there's a root at 1/2. Okay, the next thing I want you to be able to do is find the y-intercept. Always nice to be able to find the y-intercept. This one's pretty nice. Rather than set it equal to 0, this is just where we plug in 0 for x and solve for y. So plugging in 0 to my function, hopefully you have it written down on your paper. I have it over here. Plug in 0, and we can solve it out. And we get -1/3. So this is where I said I like the y-intercept being given as a coordinate. X-intercepts, you can always just say x equals y-intercept. We'll say it is 0, -1/3. That's my y-intercept. Okay, so the next thing, scrolling down, I want you to be able to find, if you remember, these things have something called vertical asymptotes. I asked a lot of you guys about vertical asymptotes on your log function. Sometimes there's going to be more than one. How do you find the vertical asymptote? Well, the vertical asymptote happens when the denominator equals 0, because then your function goes undefined and it shoots up and shoots down. It gets really, really, really big. So as you get the bottom closer and closer to 0, that means the top of the fraction is much bigger than the bottom, and that causes the number to get really, really, really big. So we're going to spend a lot of time going back to vertical asymptotes when we begin limits. I'll show you some more things about that. But for now, you need to know how to find it. It's where the function is undefined. So where g of x is undefined. And to find where any function is undefined, this is where you might have heard set the denominator equal to 0. So long story short, you can set the denominator equal to 0. So going back, we have our simplified denominator. Here it is again. X plus 3 was our denominator. So we're just going to set that equal to 0. And lo and behold, we get the location of our vertical asymptote given as an x. X equals -3. Definitely fine to give me that notation right there. And finally, the fifth thing, and this is the one that we're going to have to practice a lot together and see what you guys can remember kind of together. But the fifth thing I want you to be able to find is the horizontal asymptote. And I'm not going to use that term as much. I'm going to start to use another term called end behavior. End behavior. That means as the function x, the x value in the function goes out to infinity, gets bigger and bigger and bigger and bigger, what y value am I getting closer and closer and closer to? That's what a horizontal asymptote tends to work. This is where you have your 3 rules. And I'm not going to go into huge detail on that right now. We are going to go back to it later. But when we're talking about horizontal asymptotes, it helps to graph it in this case until you start to remember the rules. So I'm actually okay with you graphing it until you remember how the rules work, because it's a lot to digest already. But I will remind you in this case, I'm not going to give you all the rules right now because that'd be a lot to write. Coming back to the function, I wrote it right here. To find the horizontal asymptote, this is one case where if the powers are the same, so this is a case where if you notice the x is to the first and the x is to the first, when the powers are the same, so that's what's going on in this problem. If the powers are the same, so the same degree in the numerator and the denominator. So if that's the case, which is happening in this problem, you're going to divide the coefficients. So this is where we divide our coefficients. We're literally just going to divide 2 divided by 1, divide the leading coefficients, and you get 2. So in this case, the horizontal asymptote is at 2. Okay? And we are going to stop with that for now in terms of the things I want you to find. I taught some of you guys in Integrate 3 last year a way cooler way to write this using limits. But since we're learning about limits in this class, I'm not going to do that right now. We will talk about the better way to write end behavior when we get to the limit portion. But let's recap what I learned in this problem. I learned that there was a whole at 1 1/4. I learned that there was a root at 1/2. I learned that there was a y-intercept at -1/3, vertical asymptote at -3, and the end behavior or the horizontal asymptote was y = 2. So now, when I graph this thing, I'm actually going to graph the original because I want to be able to see the whole. So I know you can't see it on your screen, but I'm going to write it on my other one, and then I'll show it to you. So it was 2x squared minus 3x. And again, I'm going to keep hammering this idea home. You can use Desmos. I would, because I'm going to, jump through a lot of things that we haven't done for months. And rather than sit there and stress out because you don't remember, look at Desmos. It can answer some questions. Okay, so ready? Remember these things we found. Whole at 1. Ready? First things first. Here we go. Do we have a whole at 1? Doesn't look like it. What the heck? I thought there's supposed to be a whole. Well, if you actually go to it, come on. Oh, it doesn't want to let me. Let's go closer. Oh, interesting. Come on. There it was. Oh, you saw it for a second. It's there. Why are you being so difficult? It was there. There it is. That was weird. Yeah, undefined. The graph goes totally normal. Actually, and this is going to be a limit thing. I can't reach up there. It approaches from both sides. But right at that instant, there is no function value. It's undefined. Okay, so that works out. Other things we found. I have it on my other screen. You don't, but that's fine. You can look back. We found a root at 1/2. Does that look logical? Yes, it does. There it is, our root at 1/2. Other things, we found a y-intercept at -1/3. There it is. Very nice. We found a vertical asymptote at -3. Was that going on in this problem? I really hope so. It is. Look at that. Let's zoom way out. Right at -3, vertical asymptote. That means as this graph gets closer and closer and closer to -3, so if you plugged in -2.9999999, that would make the denominator super small and the numerator super negative, and it would shoot up like this. Or down this way. This side would shoot up. So the asymptotes just cause the graph to get really messy. And that's kind of what we study rational functions for, so that we can start to study asymptotes a little bit. So some other functions like logs and tangent have asymptotes too, but rational functions are great because we can kind of control where we put them. And then horizontal asymptote, the end behavior, you told me it was y = 2, or I told you it was y = 2. Let's see. That means as the graph goes out and out and out and out, I wonder if I can do this. Ready? No, I can't drag it. But look, as x gets bigger and bigger and bigger and bigger, look what value it's approaching. So as x gets bigger and bigger, y is getting closer and closer and closer and closer to 2. Does it ever hit it? You're like, surely it must. Well, if we were in my class and we had the graphing calculator, I would actually make you do this with me on your table, but we're not going to do it. We can do it in Desmos. So look, it looks like it really wants to, but it doesn't. It just keeps getting closer and closer. It's never going to get there because with the fact that you're dividing these terms as we go to infinity. As you plug in really, really, really big x's, it's almost like these back terms don't matter. So the way we're going to start to think about it when we get to limits is as you get x really big, as x gets bigger and bigger and bigger and bigger, only term that matters is the highest powered term in each the top and the bottom. So the minus 3x almost doesn't even affect anything. The plus 2x doesn't really affect anything. It's the x squared and the x squared that affects things. So it's almost like you can ignore the back half of it and just look at this as like it's 2x squared over x squared, which is just 2. So at infinity, this equals 2, but you can never get to infinity. That's why it's approaching 2. That's why it's called end behavior and not an actual value. All right, so that's the first problem. If you think you have it from that, you can move along. I am going to include a second problem just to, oh, that's kind of cool. Check this out. Just to kind of go through one more with you quickly. There's a summary of everything we did. How nice. Clean. I'm about to delete that though. All right, so let's do one more. Like I said, if you got it, that's 15 minutes, 16 minutes. You can move along. I'm going to do one more problem. We'll do h of x. So h of x equals, the other one I had was a little bit nicer, x plus 1 over x squared minus 1. So I'm going to keep telling you guys to be honest with yourself in this class. One option may be to try this one on your own without me quickly in your notes and then see how you did by checking back. That's one option. If you feel comfortable about it, I'm not going to sit there and say, hey, do this problem with me for the entire time. This year, you can kind of choose your level. But if you're like, no, I need to see one more of these, then see one more with me. So first thing, always factor. Top doesn't factor. That's going to happen. So we're not going to get to too crazy of bizarre ones. You may have seen some really crazy ones last year. This one's pretty tame. The bottom is a difference of squares. And nice, something cancels as it should. So I'll come down here. Nothing left up top. Please don't put 0 up top. If there's nothing left up top, you need a placeholder 1. If you said it's 0, because think about it, it's this thing times 1, really. So there is a 1. It's not a 0, because then the fraction would just equal 0. So this is our simplified function. But that means the first thing for holes or removable discontinuities, we can set the term equal to 0, and there better be a hole at -1, which means if I plug -1 into this function, 1 over x minus 1, I get -1/2. So I know that there is a hole at -1, -1/2. That's the coordinate. Sometimes I just want the x. Sometimes I'm going to want both. All right, the second thing. The roots. Well, we set the numerator equal to 0. We learned that's kind of a cool shortcut. Actually, let's just start by setting the whole function equal to 0 first. So one of the strategies is to try to multiply by the denominator, or like I said, you could just set the numerator equal to 0. And you get this. And then this is u, because you feel like you broke everything, and 1 does not equal 0. And what's this mean? Well, that's absurd. That means there are no roots. Okay, so no, you didn't break anything. 1 does not equal 0. That just means there are no roots. Okay, it means this thing, when we graph it, had better never cross the x-axis. No roots. It's never a place where the function equals 0. It doesn't happen in this problem. So the third thing, let's find that y-intercept. I like finding the y-intercept because it just gives you another free point on the graph. Because, oops, this is h. Typically plugging in 0 is something pretty easy to do. A lot of times in this class, we're going to set things equal to 0, and a lot of times we're going to plug in 0. So you plug in 0, you get 1 over 0 minus 1, or -1. So our y-intercept is 0, -1. Nice. Fourth thing, let's use this fun pen, because look at this. That's too much. I hate that. Let's never do that again. The fourth thing, the vertical asymptote. That's what we get for trying to have fun. The vertical asymptote is going to be when you set the denominator equal to 0. So the denominator was x minus 1. So I set x minus 1 equal to 0, which means x equals 1. We have a vertical asymptote. And the last one, I'm going to actually zoom out a little bit. think that's fine. The fifth thing, going back to green, the horizontal asymptote, your end behavior. So this is another case because look, the powers are not the same. So right here, I mean, you actually can look at either one in this case, but the powers are not the same. So when they're not the same, there's a different rule. When the powers are not the same, think about what happens as x gets bigger and bigger. So if I plug in 5, I get 1/4. As I plug in 10, I get 1/9. As I plug in 100, I get 1/99. If I plug in 1,000, I get 1/999. As x gets bigger, the top's not changing, but the bottom's getting bigger. So really, it's almost like the horizontal asymptote in this case is kind of like not changing 1/infinity, which seems really weird. And we're going to kind of play around with this idea. But long story short, when this happens, the end behavior or the horizontal asymptote is just, the horizontal asymptote is just y = 0. The graph is getting closer and closer and closer to 0 because the bottom is growing bigger, but the top is not changing at all. So these rules are going to be important when we get to limits. For now, if you're struggling with horizontal asymptote, just use your Desmos to help you out. So I'm going to sketch this one in Desmos. Well, I'm going to graph this one in Desmos. We'll see how we did. We will check everything. I want you checking your work. I mean, we have this amazing ability to check our work. It should never be a question of, is this right? That should be something you get for free. Check it with Desmos. Desmos is not going to make mistakes. The only mistake you make, I guess, is plugging it into Desmos incorrectly. All right, ready? I have it up here. Boom, boom. Okay, so you told me, or I told you, or we told each other, hole at -1, -1/2. So -1, no, -1. We're not going to do this again, are we? Come on. Yeah, undefined. So yes, there's not actually a point there. There's not really a coordinate at -1, -1/2. But it's almost like if there was a coordinate there, it would be -1, -1/2. And that's a big deal. When we get to limits, that's going to be a huge deal. So just keep that in mind. There's not an actual point there, but as we get closer to it, why can't I do it? As we get closer and closer, there we go. It looks like it should be a -1/2, but it's not. It is undefined. It's a hole in the graph. It is a removable discontinuity. Second thing, you told me no roots. If you show me a root, that's one of my pet peeves. If you say there's root is at 5, and then I look and there's no root at 5, I hate that. Your graph should match up with what's happening. So there's no roots, and yeah, when there's no roots, you kind of get the other one for free, by the way. No roots means that 0 is a horizontal asymptote. And look, we'll jump to that one, but look, this thing is getting closer and closer and closer and closer and closer to 0. Never actually gets to 0, though. Look how close it gets. You can sit there all night and continue scrolling if you want. Other things you told me, the y-intercept is -1, which it is. Other things you told me, vertical asymptote at 1, which, yeah, if you tried to get to 1 in this graph, you'd be sitting there all day too. You can't plug 1 into this function. It is not part of the domain. -1's not in the domain either, because if you plug in -1, you get undefined. Okay, so these guys are called rational functions. Like I said, we don't use them much for modeling. We use them when we get to more crazy combinations of functions. These are going to pop up, and you have to be able to handle any potential issues you may have with things like end behavior and asymptotes. The AP test in the past does a little bit of graphical analysis stuff, and it's usually built around these. Okay, so this is as far as we go with kind of analyzing these guys. You'll see one other case when the bigger power is in the numerator. But we're not going to talk about that one in this video. You can ask me if you don't remember during class. But good luck with these. You can sketch in Desmos. You do not have to graph these by hand in this class. So don't try to do it by hand. Just use Desmos. I am fine with that. All right, cool. That's the end of that. I'll see you guys.